You probably feel confident that you understand gravity. You step onto a weighing scale, watch the numbers settle and say, "That's my weight." It seems obvious. You imagine the earth pulling you downward, holding you firmly against its surface. It feels simple and intuitive. When you drop something, it falls. The moon circles the earth. The planets orbit the sun. Everything appears to follow a clear rule. Objects with mass attract one another. This idea, first explained by Isaac Newton, has been accepted for centuries as the explanation of gravity, and for everyday life it works remarkably well. Because of this, we grow up believing gravity is a force, like an invisible hand reaching out and pulling things together. It sounds elegant and straightforward, but here is the surprising part. This picture is not truly correct. It is not just slightly inaccurate. It fundamentally misunderstands what is really happening. Gravity is not a force in the traditional sense at all. When you begin to look deeper into the structure of reality, you discover that the universe operates in a very different way than our intuition suggests. To understand this, forget equations for a moment and focus on your own experience. Stand up and pay attention to what you actually feel. You might say, "I feel gravity pulling me down." But if you examine the sensation carefully, you will notice something interesting. The feeling is not a pull. You don't sense anything dragging you downward. Instead, you feel pressure on the soles of your feet. You feel the ground pushing upward against your body. That is the only physical sensation you can detect. This observation is important. You never directly feel gravity itself. You only feel the resistance of the surface preventing you from moving. If the ground suddenly disappeared beneath you, you would not feel a pull downward. You would feel weightless, even though gravity would still be acting. This tells us that what we interpret as weight is actually the force of the ground pushing up on us, not the earth pulling us down. The deeper explanation, revealed by Albert Einstein, is that gravity is not a force at all, but a result of curved space-time. Massive objects like the Earth change the geometry of the space around them, and everything else moves along those curves. When you are standing still on the ground, you are actually being prevented from following your natural path through this curved geometry. The ground pushes you upward, holding you in place. So what we call gravity is not an invisible pull, but the shape of the universe itself guiding motion. Once you understand this, the familiar idea of gravity changes completely. The falling of objects, the orbit of planets, and even your own weight are not caused by a force pulling you downward, but by the geometry of space-time shaping how everything moves. It is always a push, never a pull. So if you can't feel the pull, where is it? Here is something even stranger to consider. The moon is currently falling toward the Earth. It has been falling for billions of years, plummeting through the vacuum. Yet it never gets any closer. It just circles us endlessly. It is a fall that never lands. What kind of pull behaves like that? A force that tugs forever but never manages to reel the object in. Furthermore, according to Isaac Newton, this pull happens instantaneously. If you were to magically pluck the Earth out of existence, Newton's theory says the moon would feel the loss of gravity instantly across 240,000 miles of empty void. How? What carrier pigeon delivers the message? What is the mechanism? Newton himself was deeply troubled by this. He couldn't explain it. He referred to it as action at a distance. And in his private letters, he admitted that the idea of one body affecting another through a vacuum without anything else to transmit the force was an absurdity. He didn't understand how it worked. However, his mathematics were gorgeous. His predictions were flawless. Because the math worked, people stopped asking the uncomfortable questions about the how. They shouldn't have stopped asking to understand where the mistake happened. We have to travel back several centuries. Before Newton, nobody truly understood how the planets moved. Copernicus had the bold idea that they orbited the sun, which was a great start. But how? What specific paths did they trace? Enter Tycho Brahe. He wasn't just an astronomer, he was a data obsessionist. He built a massive observatory and spent decades recording the positions of the planets night after arduous night. Year after year, he measured angles with giant brass instruments, achieving precision down to tiny fractions of a degree. Why go to such lengths? Because Tycho knew that you cannot understand nature by guessing. You have to look. You have to measure with extreme care. You must write down exactly what you see, not what you want to see. That is where real science is born. His mountains of data eventually reached the hands of Johannes Kepler. Kepler was determined to unlock the secret shape of planetary orbits. He started with the assumption that they were circles, the most perfect shape. When he ran the numbers, the predictions were incredibly close to the observations, but they weren't perfect. The orbit of Mars was off by a mere 8 arc minutes. That is 860ths of a single degree. Most people, almost anyone else in history, would have shrugged that off as a measurement error, a smudge on the lens, a slip of the hand. But Kepler knew Tycho Brahe. He knew that man did not make 8 arc minute errors. He trusted the data more than his own theory. So Kepler threw out the circle. He threw out his theory and started from scratch. After years of agonizing calculation, he found the answer. Ellipses. The planets move in stretched out circles or ellipses with the sun sitting at one of the focal points. It was a perfect match to the data. It was beautiful. But it raised an even bigger, more haunting question. Why ellipses? Why that specific shape? While Kepler was gazing at the heavens, Galileo Galilei was down on Earth doing something that seemed much simpler. He was rolling balls down ramps. It sounds trivial, almost like child's play, but watch closely. When you roll a ball down a slope, it speeds up. When you let it roll onto a flat surface, it keeps going. It doesn't stop immediately. Now engage your imagination. Imagine you could eliminate all friction, no air resistance, no roughness on the floor. What would happen? The ball would roll forever. It would maintain the same speed and the same direction for eternity. This idea deeply bothered people at the time. Intuition tells us that motion requires a continuous push and that things naturally want to come to a rest. Galileo proved that intuition is backwards. Motion is the natural state. An object moving in a straight line at a constant speed needs no explanation. That is the default setting of the universe. What requires an explanation is change. If something slows down, that's friction. If something speeds up, that's a push. If something changes direction, that is a sideways force. This is the concept of inertia, the first law of motion, and it creates a massive puzzle for astronomy. If the natural state of an object is to move in a straight line, then planets should be flying off into deep space in straight lines. But they don't. They curve. Their paths bend continuously toward the sun. Something must be deflecting them at every single instant. Isaac Newton saw this clearer than anyone. Planets want to go straight. That is their inertia. But they curve. Therefore, something is changing their motion constantly. He named this influence gravity. He proposed the universal attraction between any two masses. The force depends on mass and distance. More mass equals a stronger pull. Greater distance equals a weaker pull. Specifically, the force drops off with the square of the distance. With this single principle, everything clicked into place. Why ellipses? Because planets are trying to fly past the sun. Inertia, while simultaneously falling toward it, gravity. The combination of this sideways motion and inward pull creates the elliptical path. Kepler's laws weren't just observations anymore. They emerged naturally from Newton's math. Why does the moon orbit the Earth? It is the same principle. The moon is falling toward the Earth, but it is moving sideways fast enough to keep missing us. It is falling around the Earth instead of into it. Why does an apple fall from a tree? The Earth attracts it. It is the same force, the same law, just on a different scale. Newton performed the beautiful calculation to prove this. He figured out how far the moon falls away from a straight line path every second. Then he calculated how fast objects fall here on Earth's surface. When he accounted for the distance difference, the numbers matched perfectly. This was revolutionary. It meant that the force pulling an apple to the grass is the exact same force holding the moon in the sky. Heaven and earth were no longer separate realms. They were ruled by the same physics. With Newton's law, the universe made sense. Ocean tides happen because the moon pulls on the Earth's oceans. The Earth is round but bulges at the equator because it spins. Comets return on predictable schedules because they are locked in elliptical orbits. Even strange anomalies found explanations. For instance, Jupiter's moon sometimes appeared ahead of schedule and sometimes behind. It turned out that light takes time to travel. When Earth was farther from Jupiter, the image of the moons took longer to reach us. This led to the first calculation of the speed of light. When planets wobbled slightly in their orbits, astronomers realized they were pulling on each other, not just reacting to the sun. By analyzing the wobbles in Uranus's orbit, mathematicians predicted there must be another planet out there. They pointed their telescopes where the math told them to look, and there it was, Neptune. For 200 years, Newton's law of gravity stood as the ultimate achievement in science. It explained everything anyone could measure. It was the bedrock of physics. But there was one tiny detail, one nagging thread that if pulled would unravel the whole tapestry. Drop a hammer and a feather in a vacuum. They hit the ground at the exact same time, perfectly together. Think about what that means. The hammer has much more mass than the feather. According to Newton, gravity pulls on the hammer much harder. It should be ripped down to the floor with far more force. However, the hammer also has more inertia. It is harder to get moving. It resists acceleration much more than the feather does. In Newton's view, these two effects, the stronger pull and the stronger resistance, cancel each other out. Not just roughly, but perfectly. Every object, regardless of what it is made of, falls at the exact same rate. Why? If you are enjoying this deep dive into the mysteries of the cosmos, take a second to hit the like button and share this with a friend who loves science. It helps Feynman analysis grow and keep bringing you these stories. Now back to the problem. Newton's theory requires mass to have two totally different properties. First, there is gravitational mass, which determines how strongly objects attract each other. Second, there is inertial mass, which determines how hard it is to accelerate an object. For some reason, these two distinct properties are always perfectly proportional for every substance ever tested, down to incredible precision. But why? Why should the attracting property of an object be exactly equal to its resistance to movement property? Newton had no answer. He just accepted it as a remarkable coincidence that made the mathematics work. But was it a coincidence? Decades later, Albert Einstein asked a different question. What if this equality isn't a fluke? What if this perfect synchronization is telling us something fundamental about what gravity actually is? He devised a thought experiment. Imagine you're in a closed room with no windows. You feel your normal weight pressing your feet to the floor. Now I ask you, are you sitting in a room on Earth? Or are you in a rocket ship in deep space accelerating upward at 9.8 MES squared? Can you tell the difference? If you drop a set of keys, they fall to the floor in both cases. If you throw a ball horizontally, it follows a curved path to the ground in both cases. If you stand on a scale, it reads the same number. There is no experiment you can perform inside that room to distinguish gravity from acceleration. This is known as the equivalence principle. Einstein realized that if you truly cannot tell the difference between gravity and acceleration, maybe it's because they are the same thing. Maybe what we call sitting still in a gravitational field is actually a form of acceleration. This triggered Einstein's revolution. Consider objects in free fall. An apple falling from a tree, the moon orbiting the Earth, an astronaut floating in the ISS. None of them feel any force. If you cut the cables of an elevator, the people inside float. They become weightless. They are moving naturally, following their natural paths. No forces, no pulls, nothing acting on them. But wait, the apple is clearly falling. It appears to be accelerating toward the ground. How can it have no force acting on it? Einstein's insight was profound. What if the apple isn't accelerating? What if the apple is following the straightest possible line, but space itself is curved? This is the heart of general relativity. Gravity is not a force that reaches out across empty space. Gravity is the curvature of space and time. Massive objects do not pull on other objects. Instead, they warp the fabric of the universe around them. They bend it, curve it, and distort the geometry. The apple isn't being pulled down to the grass. It is following the straightest possible path through a curved spacetime. However, near the Earth, spacetime is curved in such a way that straight ahead points toward the center of the planet. Now look at yourself again. You standing on the ground are not being pulled down. You are trying to follow your natural path through curved spacetime, a path that leads to the center of the Earth, but the ground is in your way. The floor pushes you upward, preventing you from following that natural trajectory. That sensation of weight, that isn't gravity pulling you down. That is the ground pushing you up, accelerating you off your natural path. You are being constantly deflected from your destiny. Einstein made a concrete prediction to prove this wild idea. If gravity is really just curved space-time, then light itself should be affected. Light has no mass. In Newton's theory, gravity shouldn't touch it. But if space itself is curved, then a beam of light trying to go straight must follow the curve. It should bend. During a total solar eclipse in 1919, astronomers measured the positions of stars located near the sun's edge. The stars appeared displaced from their true positions. The starlight had bent as it passed through the curved space around the sun, exactly as Einstein had predicted. This is gravitational lensing. We see it in our telescopes today. Snorts. Massive galaxy clusters bend the light from objects behind them, creating distorted arcs and rings. It is direct visual evidence that space itself is malleable. Think about astronauts in orbit. They look weightless floating around the cabin. We often say there is zero gravity up there. That is completely wrong. The gravitational field at the altitude of the space station is about 90% as strong as it is here on the surface. If gravity were turned off, they would fly away into deep space. So why do they float? Because they are falling. The station, the astronauts, the air inside. It is all falling toward Earth constantly. But like the moon, they are moving sideways at 17,000 diametramp. As they fall, the curve of the Earth falls away beneath them at the same rate. They are in a state of perpetual free fall. Since everything is falling together, there is no sensation of weight. It feels exactly like floating in empty space because physically the two states are identical. In free fall, you are surrendering to the geometry of the universe. This geometry explains everything. Why is the Earth round? Not because a force crushed it into a ball, but because space-time curves equally in all directions around the center of mass. Matter simply settles into the shape dictated by that curvature. A sphere is the only shape where every point on the surface is equidistant from the center of the warp. We have to remember it isn't just space that curves, it is time as well. We live in a four-dimensional fabric called space-time. Massive objects create depressions or wells in this fabric. The sun creates a deep well. The Earth creates a smaller one. Even you create a tiny dimple in space-time. Objects moving near these wells follow the curvature. The moon doesn't orbit because of a tether. It orbits because the straightest line it can travel in this curved environment happens to be a circle. When you throw a ball, it traces an arc. To you, it looks like a curve. But in the 4D geometry of space-time, that ball is taking the straightest possible route. It is us standing on the ground who are following the unnatural curved path through time by refusing to fall. In Newton's picture, you are static, held by balanced forces. In Einstein's picture, you are accelerating. You are like a person standing in a rocket ship that is blasting upward. The floor hits your feet, continuously pushing you away from the natural path of free fall. This is why when you trip and fall, you feel a sudden rush of relief, physics-wise at least. For that brief second before you hit the ground, you are free. You are no longer being accelerated. You are finally doing what the universe wants you to do. Once you grasp that gravity is geometry, the most extreme phenomena in the universe, begin to make sense. Consider a star. It is a massive ball of gas creating a deep gravity well. It wants to collapse inward along the natural paths of space-time. Most people are quite sure they understand gravity. You step onto a scale, watch the reading stabilize, and think, that's my weight. It feels straightforward. You picture the Earth pulling you downward, keeping you anchored to its surface. This explanation seems natural. When you drop an object, it falls. The moon moves around the Earth. The planets revolve around the sun. Everything appears to follow a simple rule. Masses attract each other. This idea, famously described by Isaac Newton, has shaped our understanding for centuries and works very well for most everyday situations. Because of this, we grow up believing gravity is a force, almost like an invisible rope pulling everything together. It feels neat and logical. But here's the surprising truth. This picture is not entirely correct. It's not just a small mistake. It misses the deeper reality of how the universe works. Gravity, as we usually imagine it, is not actually a force in the traditional sense. When you begin to explore physics more deeply, you realize that reality is far more complex and fascinating than our intuition suggests. To get closer to the truth, set aside formulas and focus on your own experience. Stand still and notice what you actually feel. You might instinctively say, I feel gravity pulling me down. But look more carefully. Do you really feel a pull? Not quite. What you actually notice is pressure under your feet. The ground is pushing upward against you. That upward push is the only physical sensation you directly experience. This detail is important. You never truly feel gravity itself. What you feel is the support of the surface stopping you from moving. If the ground beneath you suddenly vanished, you wouldn't feel a downward tug. Instead, you would feel weightless, even though gravity would still be present. This shows that what we call weight is not the earth pulling you down, but the ground pushing you up and preventing your motion. A deeper understanding comes from the work of Albert Einstein. According to his theory, gravity is not a force at all, but a result of the curvature of space-time. Massive objects like the earth bend the fabric of space and time around them. Objects then move along these curves naturally, following paths shaped by this geometry. In other words, they are not being pulled. They are simply moving along the structure of the universe. When you are standing on the ground, you are actually being held back from your natural path through curved space-time. The ground pushes against you, keeping you from freely following that path. This resistance is what creates the sensation of weight. So gravity is not an invisible force reaching out and pulling objects together. Instead, it is the shape of space-time itself guiding motion. Once you understand this, everything changes. Falling objects, planetary orbits, and even your own weight are all the result of geometry, not force. The universe is not pulling things together. It is shaping the paths they follow. And that makes gravity far more fascinating than it first appears.